Hi everyone and welcome back to PrepFusion. So today we will start with the lecture 62 of electrical machines subject. So today we will solve the assignment 21 solutions, whichever questions I gave you as homework. Also we will understand the slot harmonics, okay, in alternators. So let's start with the questions basically. So this was the first question that I gave you as homework here. So, when rotor, stator and rotor windings of a two-pole rotating electrical machine are excited, each would produce a sinusoidal MMF. So, rotor and stator windings of a two-pole rotating machine are excited. Okay, rotor and stator windings both are excited. Each would produce sinusoidal MMF. Okay, distribution in the air gap. So, each are producing sinusoidal MMF in the air gap with peak values Fs and Fr. So, for the stator it is Fs and for the rotor it is Fr. So they are producing sinusoidal MMF, and what happens in sinusoidal MMF? Basically, it generates a rotating pole. It generates a rotating pole, right? That is what happens in a sinusoidal MMF in the air gap. The rotor MMF lags the stator MMF by a space angle delta at any instant as shown in the figure. So there is a lag between the rotor MMF. So the rotor MMF, let's assume this is the rotor MMF and the stator MMF is this. So the rotor MMF will lag the stator MMF by delta. Okay. Thus, half of the stator and rotor surface will form one pole with the other half forming the second pole. So one half will totally make, like one half will make one pole, other half will make other pole. Same for rotor and same for the stator. So this half, let's assume this is north pole, then this will be south pole. Okay. Further, the direction of the torque acting on the rotor can be clockwise or counterclockwise. So rotor, right, due to the alignment torque, because both are developing a rotating magnetic field, due to the alignment torque, the direction of the torque can be both clockwise and anti-clockwise. What they're asking. So the following table gives four sets of statements as regards to poles and torque. Select the correct set corresponding to the MMF axis as shown in the figure. Okay. So they are telling me that stator surface ABC forms. So ABC is here, right? So stator surface ABC. So stator surface ABC, it will form north pole. So if the stator surface, so this is the one half, right? This is one half. Okay, this is one half, and so stator surface ABC forms north pole. They are telling me stator surface ABC will form north pole. Okay, and the stator surface CDA. So C is here, D is here, A is here, right? So CDA will form south pole. Okay, fine. So this end is south, this end is north pole. So rotor surface ABC forms north pole. So rotor surface, they are telling me ABC will form a north pole. So ABC is here, small ABC is here. Okay. Just hold on. So this is A, this is B, this is C, right? So ABC is here. This will form a north pole, and rotor surface CDA forms south pole. So this will form a south pole, they're telling me. So if this is south pole, so torque is clockwise, they're telling me. So will this work actually? This will not work, right? Because what we remember is, we remember in a synchronous machine, there is a concept of alignment torque. Alignment torque. And what is alignment torque? What is alignment torque? So alignment torque is basically when my north pole and south pole are aligned, right? North pole of the stator and the south pole of the rotor. This already have been discussed previously. And the south pole of the stator and the north pole of the rotor are together. Here are they forming together? No. Here north pole of the stator and north pole of the rotor is there, and here south pole of the stator and south pole of the rotor is there. So this is wrong, right? So no torque will be produced in option A. Okay. One more thing is, we know that the in a synchronous machine the rotor MMF follows stator MMF. Okay, this will always happen. Rotor will follow the stator. So if we see here, some axis is given, right? So the rotor will always follow the stator. So the rotor MMF lags the stator MMF by delta, right? It will lag. So I have to go in the clockwise direction to reach rotor MMF. So rotor actually will always follow the stator MMF. So always the torque actually will be in the anti-clockwise direction only, counterclockwise. So already clockwise options are gone. So counterclockwise can be a possibility, counterclockwise can be a possibility, because rotor MMF always will follow the stator MMF. Okay, rotor MMF always follows the stator MMF for synchronous machine to work. Okay, so hence it will be always counterclockwise. Now here I am seeing that like this is not alignment torque, right? So now if I change this, so if I make this south pole, this north pole, right, what will happen? So this will be, so the stator, now this will become south pole and this will become north pole, stator, right? This will become north pole. Now will this work? Again, what do you notice? What is the axis here? So the axis is like this. Axis always goes from north to south, right? If N is here, S is here, the MMF axis is along the, from it starts from N, terminates at S, right? So here the axis of the stator MMF is on the left hand side, but actually in the diagram it is on the right hand side. So it is just the opposite. It is just the opposite. So previously actually it was correct. If this was north and this was south, if this was north and this was south, then the axis would have been on the right hand side, right? It was correct, but problem was there was no alignment torque. So this option is also gone wrong. Okay, this option is wrong. Why? Because the FS direction is wrong. Now let's solve the third one. So third one, north south pole is there in the stator and the stator side, but they are interchanging the north and south pole in the rotor side. So this will be south pole and this will be north pole. Okay, this will be south pole and this will be north pole. So now if you observe, now the axis okay, this is alignment torque, this is alignment torque, there is no problem with that, but still the axis is actually wrong, right? It is wrong. This axis should be somewhere, rotor ABC is south pole. Okay, so the axis actually is somewhere here. This direction is again wrong actually. Okay, something is wrong. Actually this is a gate PY, so something is wrong here. Okay, which I am not able to figure out right now, but this question I will look into it. You can put in the comments below if you feel something is wrong, because this is a gate PY. Okay, so something is wrong with this direction, but according to me the answer would have been C, but I don't know. Now I don't know, I am also confused. Seems like question is wrong. Okay, because this MMF direction is wrong, so I will say answer is nothing. Okay, don't know the answer. So yeah, seems like question is wrong. Let's solve the next one. In a three-phase alternator, which one of the following conditions will cause reversal of the phase sequence? So how will the phase sequence be reversed? Okay, because we were discussing about the construction, so all these questions we will discuss. Reversing the field current while keeping the direction of rotation unchanged. So if I reverse the field current direction, will the direction of rotation change? No, right? Why? Basically they are telling me how can I reverse the phase sequence of the alternator. So if I have an alternator over here, if I have an alternator over here, then this will be A, this will be B phase, then I will have, so B phase will be somewhere here and C phase will be somewhere here, then A dash will be somewhere here, your B dash will be somewhere here, your C dash will be somewhere here, right? And this will be your north and south pole. North and south pole. Okay. So if I interchange the field winding connection, DC connection, this north and south pole will be changed. But still, what they're telling me, by keeping the same direction rotation. So still I am rotating in the same. This was north, this was south, and let's say I am rotating in the clockwise direction. And if I just do the same thing, if I just interchange the north and south pole, will it change anything? No, right? Again in the next half cycle, I will reach north pole. That is not a problem, right? So this is just rotating. It is just 180 degree phase shift rate, right? So there will not be phase sequence change. If I keep the direction of rotation same, there will not be phase sequence change. Okay, so changing the north and south pole will not change anything. Changing the north and south pole will not change anything. Why? Because let's say if I just observe in the coil A, okay, this is A, this is A dash, right? A dash. So what will, at, let's say at t equal to 0, I know from the north pole magnetic flux lines come out. So at t equal to 0, coil A will observe what? Maximum maximum EMF, sorry, maximum flux. That means it will feel maximum induced EMF. Okay, positive. It is going into the coil. For the same case at t equal to 0, what will happen? For south pole, right, what happens? The magnetic flux lines come in. It is, so it is coming out, so it will observe the minimum flux. That means the minimum induced EMF. Minimum means more negative. So basically here the phase difference will be phase difference will be 180 degrees. Okay, here the phase difference will be 180 degrees. So phase difference will be 180. So but phase sequence will not change. Basically your voltage, if it was plus Vm sin omega t, it will be minus Vm sin omega t. But so your V of t, right, V dash of t will be minus of V of t. Okay, but everything else will be same. That's it. Okay, so changing north and south will not change the phase sequence. Keeping the field current unchanged but reversing the direction of rotation. Yes. Why? Because let's say at t equals to 0, phase A, coil A was experiencing maximum magnetic flux. At t equal to, let's say at certain time t equals to t1, then this pole will rotate here, right? This pole will rotate here. I will copy this. Okay, and let's assume that this is coil B. So and if I rotate the poles, just give me 1 second. If I rotate it, now my coil B will experience the maximum flux at t equals to t1, and then finally coil C will experience the maximum flux. If I change the direction of rotation, what will happen? Initially coil A will experience the maximum flux, then I will next hit coil C. So then coil C will experience. Here coil B was experiencing the maximum flux, then coil C will experience. And we know phase sequence is determined by which coil experiences the peak first. So if you remember the three phase, right, I will just draw the three phase voltage waveform. This will be omega t. This will be let's assume induced EMF E, okay, in all the three phases. So here this is let's say sine omega t, okay, and then the coil B will lag by 120, so 120 will be somewhere here. Let me color this differently, and then 120 another, so it will be 240, right? 240 will be somewhere, I guess, here, something like this. I actually, is it, yeah, it is correct only, yeah, it is correct. So how is phase sequence determined? So phase sequence is determined by the peak. So whose peak comes first? So here A, B, C, okay, so here also A, B, then C, right? But here if I rotate in the anti-clockwise, first A will come, then C will come, then B will come, right? So that's why the phase sequence changes. So if I reverse the direction of rotation, phase sequence will change. So reversing field current, doubling number of poles, no. Doubling number of poles without changing the direction of field current, no. Only reversing the direction of rotation will change the phase sequence. Okay, let's solve the next question. Two alternators are mechanically coupled to operate at electrical frequencies 50 Hz and 60 Hz respectively. What is the maximum possible speed in RPM of either alternator? Okay, so two alternators are mechanically coupled to operate at frequencies 50 Hz and 60 Hz. What is the maximum possible speed of either alternators, right? Maximum possible speed that they're asking. So the two alternators are mechanically coupled. So basically, if I have an alternator here, they are mechanically coupled, means their shafts, right, are rotating together. That means their speed will be same. Their speeds nr1 will be equals to nr2. That is nr1, ns1 will be equals to ns2, because in case of synchronous machines, the synchronous speed is equals to the rotor speed. So what is ns1? ns1 is 120 into f1 divided by p1 will be equals to 120 into f2 divided by p2. Now I know that what is my f1? f1 is 50 Hz, right? f1 is 50 Hz. So 120 will get cancelled. 50 divided by f2 is 6, right? 5 by 6. So p1 by p2 is 5 by 6. Now remember this thing, p1 by p2 is 5 by 6, okay? And I already know the poles always occurs in pairs. Poles always will occur in pairs. So poles will always occur in pairs. So I can say that, of course, 5 is not possible. P1 equals to 5 is not possible. So what is the next even number? So 5 into 2. So if P1 is equals to 10, that is possible. So P2 will be equals to 12, that is possible. So what they are asking, what is the maximum possible speed? So P1 and P2 we have got as 10 and 12. Why am I choosing the minimum possible value? Because what is my speed? Speed ns is equals to 120 f by p. So if I have to find out the maximum possible speed, the number of poles should be the lowest, right? I cannot choose 5 poles. Poles first of all has to be integer, and I cannot choose 5 because poles occur in pairs. So minimum pole that I can choose. So minimum pole, right? Here I am choosing the minimum pole to get the maximum speed. Okay, so this will be basically so which will provide me the maximum speed? Both of them will have same speed only, because I have just equated the speeds, right? So one combination you take. So I will take f1. So 120 into f1 is 50 divided by 10 p1. So it will be 5 into 120, that is 600 rpm. Am I correct? Sorry, 6000 rpm. Okay, because I have another 0, so it will be 6000 rpm. 6000 rpm will be the, sorry, am I correct here? Sorry, okay, sorry, 10 will, sorry, this is 600 rpm. What am I doing? 600 rpm only. So 600 rpm will be the answer. Okay, 600 rpm will be the answer for this particular question. Very simple but elegant question. Okay, so let's now solve the next one. So these are few questions were on fundamental operating principle of synchronous motors and generators. Let's now solve this one. A 4-pole 50 hertz synchronous generator. So it is a 4-pole 50 hertz. F is equals to 50 hertz synchronous generator equipped with double layer winding distributed across 48 slots. So S equals to 48 slots. Okay, each coil consists of 10 turns. So each coil has 10 turns. So T equals to 10. Okay, is short pitched by 36 degrees. So it is short pitched by 36 degree. So basically indirectly they're giving you the alpha. Alpha is equals to 36 degree by 36 degree. Short pitch by 36. That means indirectly they are giving you alpha. Okay. Also it is double layer winding. Okay. Double layer winding. Double layer winding. All the information you have to write down. Double layer winding. The fundamental flux per pole, basically the fundamental component flux per pole is 0.025. So flux per pole fundamental component is 0.025. Okay, so that also I forgot to mention here. So whenever you are writing harmonics, right, in the previous lecture I forgot to mention, whenever you are writing, okay, I missed a point. This should be phi. Okay, I forgot to write. Phi also will come, and this phi will be phi n. So the nth harmonic will have different flux component, right? Fundamental will have the highest flux component, nth harmonic will have different flux component. Okay, phi n m, the peak value of the flux, right? This I forgot to write in the previous lecture. So yeah, this will be there in the formula. So let's now solve this. What is the approximate line to line induced EMF for the 3-phase star connected system? Okay, so line to line induced EMF they are asking. So first of all, I will calculate the phase induced EMF. What is phase induced EMF? It is root 2 pi f into phi m into number of turns per phase. Okay, remember it is per phase number of turns into the pitch factor into the winding distribution. Distribution factor, right? So how many total number of turns I have? Each coil has 10 turns. Okay, each coil has 10 turns, and I have total. It is double layer. It is double layer. I have total 48 slots. So how many total number of coils I will have? So as it is double layer, so I have 48 slots, right? So as it is double layer, if you remember, the number of slots and the number of coils will be equal. Okay, so it is double layer, right? So each slot will contain 2 coil sides, right? So I have, it is double layer, so 1 2, so each slot will contain 2 coil sides. 2 coil sides basically. I hope you have revised the previous lecture. So 2 coil sides meaning one coil. So the total number of coils will be total number of slots, that is 48. I have 48 slots. Total number of slots is 48. Okay, clear? That is my total number. Sorry, total number of coils is 48. So each coil has 10 turns, right? What is the total number of turns? N total. It will be 48 into 10. So that will be equals to 480. 48 into 10 will be equals to 480. Okay, that is the total number of turns. Now what is the turns per phase, right? Per phase how many turns I have? So per phase turns you have to find out. So it will be, it is a 3-phase machine, so it will be 480 divided by 3. So it will be 160. So 160 turns per phase. Okay, that is the number of turns per phase I have. So I have got my per phase number of turns. What is my Kp? So for fundamental Kp will be cos alpha by 2. So cos of alpha is 36. divided by 2. So cos of 18, right? What will be cos of 18? Cos of 18 will be 0.951. And what will be KD? KD, if you remember, it was sine of m beta by 2 divided by m sine beta by 2. Okay, so now uh, now okay, what is my beta? Beta, if you remember, was the pi upon slot per pole, right? So these things you have to remember. Okay, beta was basically the how much slot span there is. It is slot span, right? So it was pi upon slot by pole. So this will be pi. I can write this in degrees as well, no problem. Number of slots, how many slots I have? Total number of slots is 48. How many poles I have? A number of poles is 4. So this will be 180 divided by 12. So it is 15 degrees. So beta is 15 degrees. So what is m? M is basically slots divided by number of poles into number of phase, right? 3. So slot by pole is for 12. 12 divided by 3 will be 4. So KD will be equals to sine of m beta by 2. So 4 into 15 by 2 degrees divided by m into sine beta by 2 degrees. Okay, so this will be 30 sine divided by 7.5 sine divided by 4. So KD comes out to be 0.9576. Okay, so basically my E phase will be equals to this 4.44 into 50 hertz. It is a 50 hertz machine, right? F is 50 hertz into phi m is 0.025 into the number of turns per phase, that is 160, into kp into kd. Kp is 0.951 into kd is 0.9576. okay, so this will be into 0.951 into 160 into 0.025 into 50 into 4.44. So this will be 808.73 volts, 734 volts. It is phase voltage, but they have asked me the line voltage, so I have to multiply root 3. So E line, right, induced line voltage will be 1400.77 volts. So this will be the answer for the question, 1400.77 volts. So this is the first part actually. So they have asked few more things actually. What are they asked? Now they are asking, remember this is what, here your m comes out to be greater than 1, that means it is distributed. It is distributed winding. Okay, now let's like solve the next part of this question. They are asking what is the approximate line to line voltage for a two phase connection. Okay, it is very interesting. If it is a two phase connection, then what will be the approximate line to line voltage? So here, right, what is the number of phase? Number of phase is 2. Okay, if the number of phase is 2, for it, like this information you should know, for a two phase connection, the phase difference, okay, this if you don't know, now you know that the phase difference between the two phases will be 90 degrees. It will not be 180. Okay, it will be 90. Okay, so this will be E phase, this will be E phase, right? So For a two-phase system, the phase difference will be 90. Now, what will be the resultant voltage? Resultant will be somewhere in between. And what will be the value? Just follow the Pythagoras theorem. It will be root 2 into E phase, right? E phase whole square plus E phase whole square under root, right? Root 2 into E phase. So this thing you have to understand. This thing you have to understand. For a two-phase system, this you have to remember. I think in basics of network, somewhere I mentioned for a two-phase system, the phase difference is 90 degrees. Okay. I also tend to forget this, but now I hope you know. So for a two-phase system, the phase difference is 90 degrees. So will the E phase change? So what will be the E phase now? E phase formula will be same. 4.44 into F into pi phi into number of turns per phase. Now number of turns per phase also has changed into Kp. Kp will it change? Kp will not change, but Kd will change. Why Kd will change? I will explain. So what is the number of turns per phase? So total number of turns is 480, correct? Number of turns per phase will be 480 divided by 2, 240. So number of turns per phase has changed. Kp is same. Kp will be cos of alpha by 2, which is same. 0.95 whatever we have calculated. So I will copy those values, right? I'll copy these values. Let me, yeah. But your M will change, right? If your M changes, then your Kd also will change. Okay, so your beta will be what? Beta will be S by P. So number of slots has not changed, number of poles has not changed, so this will be same, but your aim will change. It is number of slots per pole per phase, so this will become 2 now. So this will be 2, so this will be 6. Okay, still it is distributed, but M has changed, so this will be what? Sine of M beta 6 into 15 divided by 2 divided by 6 into sine beta by 2. So the Kd will further reduce actually, you will see. So this will be sine 45 actually. So sine 45 sine divided by 6 into 7.5 sine, okay, not into actually, sorry. So 6 into 7.5 sine into 45 sine. Okay, so this will be 0.9029. Okay, so this will be the Kd has reduced slightly. So now I will write my E phase, right? Per phase induced EMF. So per phase induced EMF, will be, E phase will be sine M beta. So here write 4.44 into 50 into 0.025 into the flux into the number of turns per phase 240 into Kp. Kp will not change, Kp will be same, that is 0.951, but Kd will change 0.929. So my E phase will be this into 0.951 into 240 into 0.025 into 50 into 4.44. So this is 1143.723 volts. Okay, so what will be my line voltage in a two-phase system? Root 2 times this. So it will be root 2 times this. Actually line voltage has now increased. So it is 1617.47 volts. So this will be the answer for the second part of this question. Now if I move to the third part of this question, what happens? So in the third part, they're telling me what is the value of the fifth harmonic component of the phase EMF for the three-phase connection. Okay, what will be the third harmonic component? Okay, so the here, right, actually they have not given me the third harmonic component of the flux, so I have to choose. Okay, so for this, right, what will be the third harmonic component of the, sorry, fifth harmonic component of the phase voltage? It will be root 2 pi into 5f, because fifth harmonic will have frequency of 5f, into the flux of the peak flux of the fifth harmonic. So that's why 5m into number of turns per phase into kp5 due to the fifth harmonic and kd5. So you will say, sir, I will need this value. You're correct, but actually something interesting happens over here. The interesting fact is, what is kp5? kp5 is equals to cos of 5 into alpha divided by 2. So it is cos of cos of 5 alpha. So 5 into alpha, 5 into alpha, alpha is short pitch by 36, right? So it will be 36 divided by 2. So it is 180, 210, 210 divided by 2. Okay, am I correct? Okay, so okay, this will not be 0 anyways. Okay, no, yeah, it's sorry, 5, right? So 5, 150 into, so 180 divided by 2 is cos of 90. So what is cos 90? It is 0. So basically your kp5 becomes 0. If it becomes 0, so your EMF also will be 0. So the induced EMF due to the fifth harmonic will simply be 0. So that's why you don't need this fifth harmonic component of the flux. That's the beauty of this question. Let's now solve the next question. So a three-phase stator winding has 5 slots per pole. So S is equals to S by P is equals to 5. Okay, that is given to me. It's a three-phase system. So three-phase employs coils with a span of 10 slot pitch. Okay, so the coil span is 10 slots. So a coil span, it will take 10 slots. Coil span is 10 slots. That is given to me. Okay. What else is given to me? The arithmetic sum of the induced EMF per coil is 10 volts. Okay. So now that formula actually will be useful. If you remember, the formula for Kp. So this definition, actually fundamental definition, you have to remember that the formula for Kp was vector sum of induced EMF, right, when it is short pitched, divided by the arithmetic sum. This formula you have to remember, unfortunately. This formula you have to remember. Okay, divided by arithmetic sum. Remember, arithmetic sum will always be higher than the vector sum. Okay, so if I have two quantities, let's say both of them E. Okay, the arithmetic sum is 2E, right? But the vector sum will be somewhat here, but it will not be 2E, somewhat lower than 2E. So that's why arithmetic sum always will come lower, vector sum always will come in the numerator to make Kp less than 1. Okay, so arithmetic sum of induced EMF. Okay, this is what my Kp is equals to. Okay, so what are the values of pitch factor and vector sum of the induced EMF per coil? Okay, so slot per pole per phase, sorry, I missed this term, per phase. So slots per pole per phase is 5. So what will be slots per pole? Sorry, I'm really sorry. Slots per pole will be what? Slots per pole will be 15. That is what my slots per pole will be. So slots per pole. So a whole pole, right? Whole pole is covering 15 slots, right? So a whole pole will cover 15 slots, and out of those 15 slots, 10 slots are used for the coil span. So each coil is covering how much? 10 slots, right? That is given to me in the question. If you see, that is given. Each coil is covering 10 slots. So what will be the remaining portion? Remaining, so 5 slots is actually the portion which the coil span is corded. So I know this 15 slots is what? A whole coil pole span. Pole span is how much? 180 degrees. So how much angle will be 5 slots? So 15 is 180. So 5 will be 60. 15 is 180, 5 will be 60. So I got my alpha. Alpha will be 60 degrees. So what will be my KD distribution factor? Cos of alpha divided by 2. So 60 divided by 2. So it will be equals to cos of 30. Cos of 30 is 0.866. So your distribution factor is 0.866. That is present in the option C. Also your, what they are asking, the vector sum. Vector sum will be what? Arithmetic sum into the KP. So arithmetic sum is given to me 10. So vector sum will be vector sum will be 10 into the KD 0.866. So this will be 8.66 volts. Okay, 8.66 volts. So yeah, this will be the answer basically. Option C will be the answer. This and this one. Now let's move on to the next question. So this is the next question. So a 3-phase 4-pole synchronous machine is equipped with 96 stator slots. Okay, so total number of slots is 96. It's a 4-pole machine. P is 4, 3-phase. The stator contains double layer winding. So it is double layer winding. Double layer winding. What does double layer winding means? Double layer basically means number of coils will be equals to number of slots. That is equals to 96 with 4 turns per coil. So what is the total number of turns? N total will be 96 into 4, right, which is equals to 400, that is 384. Okay, this will be the total number of turns. The coil pitch is 19 by 24 of the full pitch. So coil pitch is 19 by 24. So what does it actually means? So I will explain what does it actually mean. So full pitch means 1, right? Full pitch means 1. So what is the slots per pole? Slots per pole. Slots per pole is number of slots per pole. 96 divided by 4. That is actually 24. So each pole will cover 24 slots. So out of those 24 slots, right? 24 slots I have. Out of those 24 slots, only 19 slots the coil is spanning. The rest is free. So this is the coil span, right? 19. So rest this much. How many slots are free actually? So 5 slots are free. So from here I can directly find out what is alpha, right? So 24 is 180, right? Because each pole will cover 180 degrees. So how much will be 5? 5 will be basically 180 divided by 24 into 5. Okay, so this will be equals to 180 divided by 24 into 5. So this comes out to be 37.5. Okay, this is the chording angle, right? So from here I can directly write what is my Kp. So Kp will be cos of 37.5 degree divided by 2. So this will be equals to cos of 37.5 divided by 2. So 37.5 divided by 2 cos of this. So this will be 0.947. Okay, so your Kp comes out to be 0.947, but they have not asked as Kp. Okay, they have actually asked the pitch factor. That is already what we have found out. Okay, so the slot angle, what is a slot angle in both mechanical and electrical degrees, right? Slot angle. So slot angle will be basically slots per pole. So each pole, in each pole I am covering 24 degrees. So what will be the slot angle? So slot angle will be basically 24 poles means 180 degrees. So how much slot angle is beta? So how much will each pole cover? So beta will be 180 divided by 24, right? How much angle each slot covers? So 180 divided by 24. So that will be this is how much? This is actually 180 divided by 24. Am I correct? Yeah, 180 divided by 24. So this is actually 10 is not correct. I guess it is something 15 or something is coming now. So 180 divided by 24, 7.5. Remember, this is in electrical degrees. Electrical. They are asking both in electrical and mechanical. So what is theta? What is beta mechanical? It will be P by 2 into, sorry, theta, I know beta electrical is P by 2 into beta mechanical, right? So beta mechanical is equals to 2 by P. 2 by P, poles. Poles is number of poles is basically 4. So 4 into beta electrical, that is 7.5. So it will be even lower, right? So beta mechanical will be this divided by 2 basically. So this will be 3.75 degrees. So this will be the first part of the answer. Second part is the coil pitch expressed in electrical and mechanical degrees. Coil pitch, they are telling me coil pitch. So what is the coil pitch basically? So coil pitch will be, I have 19 slots in 24 slots. Okay, so how much degrees is each coil covering? That is what I want to know. So it will be basically, I know what is the amount of degrees each slot covers. Each single slot will cover 7.5 degrees. So 19 slots, because it is coil pitch is 19. So 19 slots will cover. So coil pitch, right, or span will be equals to 19 into beta, right? So beta electrical will give me electrical, beta mechanical will give me mechanical. So beta 19 into beta electrical will give me 7.5. That will be 142.5 degrees electrical, and mechanical will be 19 into 3.75. That will be just half of this. That will be 71.25 degrees mechanical. That's it. Okay, that's it. 71.25 degrees mechanical. Now this is the second part. Third part already we have calculated. Kp we have already calculated. Kp is equals to 0.947. So Kd I need to calculate. Kd is very simple, right? Kd is sine of m beta by 2 divided by m sine beta divided by 2. So what is m? M is slots per pole per phase, right? Slots per pole we have already calculated 24. Per phase will be This divided by 3, that is 8. M is 8. Beta we already know in electrical, remember. Beta electrical is 7.5. So KD will be sine of 8 into 7.5 divided by 2 divided by M, that is 8 into sine of 7.5. Okay, this will be equals to 4 into 7.5 sine divided by 8 into 7.5, sorry, wait a second, 7.5 divided by 2 sine into 8 into 4 into 7. Okay, this will not work. 8, sorry, hold on a second, 3.7.5 divided by 2 sine of this into 8 is 0.52322, and the numerator will be 8 into 7.5 divided by 2 sine of this will be 0.5. This will be 0.5 divided by 0.52322. So this will come out with 0.95562. Okay, this is the distribution factor basically. So from here I can, okay, we have already found all the answers, right? This is the distribution factor. So we got all the answers. Kp we have already found out. So Kd we just need to find out, that is 9.5562. Okay, this will be the answers for this question. So let's solve this question. So a three phase, so number of phase, it is a three phase system, 16 pole. Whenever these kind of questions come, right, you have to write the data. Okay, if you don't write down the data, then like again you have to reread the question. That will take another 10 seconds, 20 seconds. So you have to save your time. 16 pole stated with slots as 144. So I have total of 144 slots. Each slot contains 4 conductors arranged in 2 layers. So it is a double layer winding. Each slot contains 4 conductors. So what is the total number of conductors? Total conductors, each slot contains 4 conductors, and okay, and arranged in 2 layers. So here total number of slots and total number of coils will be same, right? When it is a double layer winding, total number of coils and slots are both are same. Okay, so what is the total number of conductors? So each coil will have the total, okay, let me and each slot contains 4 conductors. So each slot will contain 4 conductors. Okay, so what will be the total number of conductors? 4 into 144, right? This will be the total number of conductors. Now what they are telling, that all conductors of the given phase are connected in series. Okay, so each conductor, so what is the conductor per phase? In phase it will be total number of conductors divided by 3, because I have 3 phase. So this will be 48 into 4. So 144 divided by 3 into 4, so it comes out to be 192. Okay, conductor per phase will be 192. Now what else they are telling, that slot has 4 conductors. Okay, each slot has 4 conductors, yeah. So oh sorry, this is not conductors, right? This is number of turns. So actually I have found out number of conductors per phase, per phase, right? What is the number of turns? I know that 2 conductors will make a single turn, right? So here how many conductors I have? 2 conductors. So 2 conductors make a single turn. So if I have 192 conductors, how many number of turns will I have per phase? number of turns per phase will be 192 divided by 2, so it will be 96. Okay, this many number of turns I will have. Okay, so these are my number of turns per phase. Now number of turns per phase. Now the alternator operates at a speed of 375 rpm. So ns is 375. From here I will be able to find out the frequency, right? Frequency I will be able to find out because frequency is not given to me. So I know number of poles is 16. So it will be f will be equals to 375 into 16 divided by 120. Okay, so 375 into 16 divided by 120, so f is 50 only. Okay, indirectly f is 50. Okay, if the air gap flux is sinusoidally distributed with a magnitude of 5 into 10 raised to power minus 2 Weber, so phi flux has been given to me, 5 10 raised to power minus 2 Webers, and coil span is 150-degree electrical. So coil span is given to be 150-degree electrical. What will be the cording angle? It will be 30-degree electrical, right? So what will be the pitch factor? Kp will be cos of alpha divided by 2. So cos of 15. What is cos of 15? It is 0.9966. Okay, calculate the phase voltage induced in volts, right? What will be the phase voltage? So what is the phase voltage? Phase voltage is equals to my 4.44 into f I know, into phi I know, into n phase I know, into kp I know, into kd, distribution factor. So what is the distribution factor? So distribution factor, if you remember, kd, this is the formula based, simple formula based, sin m beta by 2 divided by m into sine of beta by 2. So what was beta? Beta was basically, if you remember it correctly, it was pi upon slots per pole. Correct? This was my beta. So pi upon slots is 144 and number of poles I have 16 pole, right? If I directly want to write the angle, right, 180 degree, this is in angle. If I want to directly calculate in angle, so in angle what will be the values of 144 divided by 16 into 180? So it is 20 degrees. Okay, it is 20 degrees. So now yeah, what will be m? M will be equals to number of slots per pole per phase. So this is already 144 divided by 16 is already 9, I guess, divided by 3, so this will be 3 only. M will be equals to 3. So as m is 3, of course it will be a distributed winding, right? So I will put the values here. So sine of 60 upon sine of 30 upon 3 into sine of 10 degrees. So 30 sine upon 3 upon sine of 10 degrees. So this is equals to 0.9596, okay, or 96 only, 96. So this is my kd. So I will replace all the values over here. So 4.44 into f into frequency into your flux, that is 5 into 10 raised to power minus 2 into n phase. So n phase will be number of turns per phase is 96 into kp is 0.966 into kd is 0.96. So now I will put all the values into 0.966 into 96 into 5 into 50 into 4.44 into 0.01. So it comes out to be 988 volts. Okay, approximately 988 volts will be the answer for this question, right? So they have asked per phase voltage induced per phase. If they would have asked line voltage, then I would have told root 3 into E phase, right? But although it is not mentioned whether it is star connected or delta connected, I will assume it to be a star connected. But they have asked per phase, so per phase will be 988 volts. Let's now solve the next one. So this will be the last question basically. After this we will start with a new topic, that is slot harmonics. So a 50 hertz salient pole, 50 hertz salient port synchronous generator with two layer means my number of slots will be equals to number of coils. Double layer, number of slots will be equals to number of coils. Full pitch means kp is 1, means your alpha is 0, right? There is no space, coil span is totally the pole pitch, so alpha is 0, that means kp is 1. Following specification, machine has following specification: diameter of the core is 7 meter. Okay, the core length equals to 1 meter. Total stator slots S equals to 600, and rated speed is ns is equals to 120 rpm, and 2 conductors per slot. So what is the total number of conductors? Total conductors will be 2 conductors per slot. So I have total 600 slots, so I will have 1200 conductors. What will be the turns per phase? It will be 1200 total conductors divided by 2, because each 2 conductors will have 1 turn, right? And divide by 3 because I am calculating per phase number of turns. So this will be 200 turns. Okay, so my number of turns per phase will be 200 turns. Okay, the air gap flux density is sinusoidal with peak value phi m to be equals to 1.2 Tesla. Okay, air gap flux density, remember they have given air gap flux density, not air gap flux. They have given air gap flux density. Again, like one formula, this formula, if you remember, like there is a derivation as well, but if you remember it, that's good. Basically your core rotor, right, is a cylindrical structure. So they're telling me that the air gap flux density is it is not bm, it is not phi m, it is bm. Bm is 1.2 Tesla. That means what is phi m? What will be the peak value of flux? How will I calculate the peak value of flux, right? So it's not that difficult to calculate the peak value of flux here. So how will you calculate? So basically this is equals to what is bm equals to? Bm equals to phi m divided by area. Okay, average area, and this area comes out to be actually 2d by p, 2d p into L by p. Okay, this I had derived in DC machines, so I am not deriving it over here again. This has been derived in DC machines. Okay, so from here I will be able to get my phi m. This formula you can remember, or you can see the derivation in DC machines. So phi m will be equals to 1.2 into 2, and diameter is given to us, that is 7 meter, and length is given to us, that is 1, and number of poles is not given to us. Okay, but the speed is given to us, right? Ns is given. So if ns is given, I will be able to find out the number of poles. So 120 will be equals to 120 f by p. Okay, number of poles is actually 50. So ns is given as 120, that will be equals to 120 f by p, that is 120 into 50 divided by poles. So number of poles will be 50. So there are 50 number of poles, quite large. So 50, right? So your flux, right, overall peak value of flux, 1.2 into 2 into 7 divided by 50, so it's 0.336 Weber. Okay, so now I know everything, so I'll put, okay, I don't know everything, so I don't know what is my distribution factor, right? KD I have to find out. So determine the maximum possible RMS voltage. Okay, they are asking me maximum possible RMS voltage that can be generated if all the conductors are connected to form a single phase winding. Okay, I have not even read the question. They are asking the maximum possible uh, RMS voltage that can be generated if all the conductors are connected in to form a single phase winding. So we are connecting a single phase winding. So case 1 is single phase winding. If it is single phase winding, then what will be the number of turns? Total number of turns will not be anymore this, right? 200. It will be 600 because each phase has 200. So total number of turns, if it is a single phase, it will have 600. Okay. Now what is my KD distribution factor? What will be my KD distribution factor? KD is again the same formula, that is sine of m beta by 2 divided by m sine beta by 2. Okay, so this will be equals to sine. Now what is m? M is slots per pole per phase. So slots per pole per phase, here phase is 1, so total number of slots is I guess total number of slots is 600 and number of poles is 50. So 600 upon 50, your m will be 12. Okay, what is your beta actually? Beta is 180 degree divided by slots per pole, right? So it is again 12. So 180 degree divided by 12, 180 divided by 12, so it is 15 degrees. Beta is 15 degrees, right? So beta is 15 degrees. So my KD will be what? Sine of m beta. So 12 into 15 divided by 2 divided by m, that is 12 sine of beta divided by 2, 15 divided by 2. So this divided by 2 sine into 12, so 1.566, and this will be 6 into 15, so 90. Sine 90 is 1 simply, right? Sine 90 is 1. So 1 divided by 1.566, which is 0. Like KD is very bad. So the distribution factor actually becomes very bad if the number of phases becomes 1. So it will be 0.6385. So now your E phase, right, E per phase for a single phase winding, it will be 4.44 into F. F is 50 into phi is 0.336. Phi will not change, right? Phi will be same, into number of turns per phase, so it will be 600. Am I correct here? Yeah, number of turns per phase, it is like single phase only, so it will be 600 into Kp is 1 because already coil span they have told me it is 1, into Kd is very low, 0.6385. So this will be the RMS value per phase for a single phase winding. So let me calculate this value. So this will be into 50 into 600 into 0.336 into 4.44. It comes out to be 28,000. So it's like some kilovolt. It's like very high value. Some kilovolt it's coming. So 28.589 kilovolt. Okay. So that is the answer for the first one. Like huge voltage it is coming. High, very high voltage. Okay. Let's now solve it for the second one. Okay. Second one, they are telling me that what will be the E phase when it is configured as a balanced three phase output. So balanced three phase, basically your M will change, right? When it is three phase winding, your M will change. What will be M? M will be slots per pole per phase. So here M was slots per pole divided by 1, which is 12, but per phase it will be 12 divided by 3, so it will be 4. Here M will be 4. And what will be your beta? Beta will be same. Beta will not change. Beta will still be 15 degrees only. It is basically 180 divided by slots per pole. So beta will not change. Beta will be still 15 degrees. Okay. Beta is still 15 degrees. Now what I can do is I can my KD will change. Everything else will remain same. Okay, N phase also will change. N phase already we have calculated. If it is a three phase winding, it will be 200, right? Everything else will be same. Okay, what will be your KD? KD will be sine of M beta. So sine of 4 into 15 divided by 2 divided by M sine of beta by 2. So this will be 4 into 15, so sine of 30 and 0.5 divided by 4 into 7.5 sine, so 0.13. Okay, so this into 4 into 0.5, so it comes out to be 0.9576. Okay, 0.9576. So this is my KD. This is my KD. Now I can write my E phase, right? E phase will be what? 4.44 into F, that is 50, into 5, that is 0.336, right? 0.336 into N phase, that is 200, into KP is 1 obviously, into KD, that is 9576. So this one has improved, but this one has reduced, right? Number of turns per phase. So your voltage also will be overall reduced. So into 200 into 0.336 into 50 into 4.44. So it comes out to be around 14.286 kilovolt. This is what your E phase will be when it is three phase balance winding. Okay, now let's quickly discuss about a very short topic, that is slot harmonics. What do we mean by slot harmonics? So what are slot harmonics? Basically, slot harmonics, let's say I have two cases. This is one of the case, this is the other case. Okay, these are the two cases I have. Now here what we need to understand is if the flux is traveling, right? If the flux is traveling, and we are assuming that flux is purely sinusoidal. So this, right, this, if coil is present over here and coil is present over here, the reluctance of these two paths will be different. So let's assume that the reluctance of this path, because here the air gap will be bit larger, here the air gap will be much smaller, correct? So the reluctance, like gap of the slot, is greater than gap of the normal without slot. Okay, without slot. So these, right, I will just delete them. These will be called teeths. Okay, and these will be called slots. Okay, so these are called teeths, these are called slots. Now the important point to note here, air gap of slots will be greater than air gap of teeth. That means the reluctance of slots will be greater than reluctance of teeth, because it is directly proportional to length. So that means flux density will be constant, but the flux of slots will be less. Than flux of teeth. Flux of slots will be less than flux of teeth. Okay, so I hope that is clear now. So now the thing is that few important points. This is the important point, right? Now if let's say everything was uniform, then here whatever flux I have, here also I have same flux, right? Here flux would have been constant. Okay, throughout flux would have been constant. I would have got a kind of a not a rectangle, not a sinusoidal, but a rectangular kind of wave. But here in certain positions the flux is lower in slots, flux is higher in teeth, then lower in slots, higher in teeth, then again it will go into the next half cycle, again lower, higher. Okay, it will be like this. So there will be, due to this, right, the waveform, we were expecting this waveform, but we are getting this waveform. So there is a bit of harmonics. Okay, so that is what we are showing. So there is a bit of harmonics. Now how do I define the harmonics? So these are called harmonic in the waveform due to slot. So these are called slot harmonics. Slot harmonics. Okay, now few important points to note here is uh, my teeth flux will be higher and slot flux will be lower. So can I calculate the time period of this variation, right? Each time I am varying like a square over the bigger waveform, can I calculate the time period? So if the whole time period is t, right, of the flux waveform, if I am passing from north to south, what will be the time period of this? How do I calculate the time period of this? Time period ts. So time period ts, right, will be equals to this. What is this much time? This much time is t by 2. And in this much time, how many slots am I covering? So basically I am covering how many slots? 3 slots in t by 2 time, because when my north pole is here, it will then rotate a whole circle, not whole circle, half a time period. South pole will be here, then the flux direction will go to negative, right? So if it rotates a half revolution, the flux direction changes across this C coil, right? So in a half duration, how many slots am I passing? It is 3 slots, right? So what is it actually? It is basically slots per pole, right? So 3 is total number of slots, that is 6. I have total number of slots. How many poles I have? 2. So basically it is slots per pole, right? So how will I calculate TS? So TS is repeating how many times? Once and twice. Okay, and 3 also should be there. Okay, sorry. Yeah, made a mistake. Now this will be this. Okay, so how many periods I'm covering? 3 periods, right? So this is one period, then another period, then another period. So 3 periods total I'm covering. So if I'm covering 3 periods, that means this will be what? Number of slots divided by pole, because this overall duration is t by 2 and totally I'm covering this 3 times, right? So this much time will be what? T by 2 divided by 3, right? Because it is getting divided in 3 parts. That's why here S by P is there. So that is the time period of slot harmonics. Okay, so what is the frequency of slot harmonics? Frequency of slot harmonics will be just the inverse of this, right? So frequency of slot harmonics will be inverse, that is S by P divided by 2 into S by P divided by T. Okay, so this, right, you can remember it or you can understand it conceptually how it came. Okay, that both are enough. So how can I actually remove it? So can you tell me which one is easier to remove, right? Which harmonics is easier to remove? Let's say I have a sinusoidal waveform, okay, and this kind of harmonics I have, okay, and I have another sinusoidal waveform. Just hold on. Okay, you are not able to see the harmonics even. Okay, so can you tell me which one is easier for me to remember? Sorry, remove. So this one will be easier because it is a high frequency noise, and I see almost it is like a sine wave only. So high frequency noise, we can easily remove high frequency noise. Okay, we can easily remove high frequency noise. That's it. So yeah, so that's why we will try to increase our slot harmonic frequency. So higher harmonics are easier for us to remember, remove, right? So we want to increase the slot slot harmonic frequency. So how can I increase? I will increase the number of slots. That will improve the waveform. Okay, so I cannot decrease the poles will be there, so I have to increase the number of slots. Okay, so by making the winding more distributed. By making the winding more distributed, I can simply reduce the slot harmonics. Okay, so one more important point is there. If about regarding the distribution winding, if I have uniform, like almost uniform distributed winding, if I have almost uniform distributed winding, that then what will happen? Then that means your M is very near to 1, right? M is very near to 1. Also, one more point, your beta also will be very less. You will see if in case of uniform distributed, beta will be very low, small, beta will be small. So if beta is small, your beta by 2 also will be small. Beta by 2 also will be small, right? So the formula Kd will change. So this is only what you have to keep in mind. Your Kd will be, if you know Kd is what? Kd is sine of m beta by 2 divided by sine of m into sine of beta by 10. Okay, so if beta by 2 is very low, right, then I can say that sine beta by 2 is equals to beta by 2, right. So then you will write your KD roughly will be sine of, now one more thing, your m beta, right, m beta is xi, the phase spread we have discussed in the previous lecture, it is equals to phase spread. So sometimes this formula is also written in few books, that it becomes sine of xi by 2 divided by, directly this becomes beta by 2, so this becomes xi by 2 into KD. Okay, okay, it is xi by 2. So this is one thing that you have to keep in mind. And one more way we reduce our uh, like, okay, slot harmonics is written over here, whatever I discussed same thing is written over here, how the undesirable components come in the air gap magnetic flux density due to the discrete nature of the stator slots and the teeths, right, between the teeths and the slots there is a discrete nature due to which the slot harmonics come. Okay, so we can increase the air gap. If I increase the air gap, if this air gap is increased, right, if this air gap is increased, then the difference between here and here will be smaller, so harmonics will be reduced by using distributed winding. Just I have explained how you can improve, basically by increasing the angle, sorry, reducing the angle beta, right, because I want to increase the number of slots. If I increase the number of slots, the beta will be reduced, right, beta value will reduce, so then the roughly the KD will be this, KD value will be this if I am increasing the number of slots. Okay, so another way to reduce the harmonics is by using fractional slot winding. So this can help reduce harmonics. Okay, how it can help I will not explain here because that is a theoretical thing. Fractional slot harmonics basically means your m, right, will be a fraction. Generally your m is integer, then it is called as integral slot winding. If it is fraction, then it will be called as fractional slot winding. Okay, so with using fractional slots we can actually reduce the harmonics. Also we can increase the slot depth, right, slot depth meaning this, right, depth means this slot depth, sorry, not increase or reduce, I think it should be reduce, I think it is reduce, right, yeah, reducing the slot depth, basically this, right, this depth. If I reduce this depth, if I reduce this distance, of course, right, this will be more closer, so the air gap will be more uniform, so air gap will be more uniform, so that will also help us in reducing the harmonics. So air gap will be more uniform, air gap length length will be more uniform. Okay, shallower slots reduce, so skewing also, you can, if I can skew the slots, okay, basically the slots are like this, okay, but somehow if I can skew the slots, then some, they can be like this, can be more uniform. Okay, that also will help. Okay, if I twist the slots, that also helps in reducing the harmonics. Okay, so these are few theoretical points that you should know. So these are the points that we can use. Okay, summary, I don't think we don't need summary because this is a theoretical thing, we don't need this. So let us solve a question basically, which is, I think, which is not kind of slot related, but it's a very old gate question. We will try to solve this question, right? So let's solve this question. A armature of a single phase alternator, okay, it's a single phase, so phi is one single phase alternator, is uniformly wound with T single turns coil. Okay, so I have T number of turns. If the RMS induced voltage in each turn is 2 volts, so RMS induced voltage per turn, so E per turn is 2 volts. Okay, so the total RMS voltage of the entire winding will be, so EMF per turn is 2 volts, that is given to me. EMF per turn is 2 volts, right? So I know this thing, right? I know what is the formula of E phase. E phase is equals to 4.44, it's a single phase winding, right, into phi into uh, the frequency into the number of turns, right? Let's say here it is T, total number of turns, into Kp into Kd. So EMF per turn is given to me. So E phase upon T is given to me already. 4.44 phi F Kp into Kd. I already know this value. 4.44 phi F Kp into Kd. I already know this value. That is equals to 2 volts. Now they're asking me what is the entire, what will be the EMF? Will it be, so the each turn is 2 volts, so will it be 2t? That is what they are asking. Is it correct here? Sorry, if the RMS voltage of the induced EMF in each turn is 2 volts. Okay, one thing is wrong here, right? Kp Kd will not be there. So yeah, here Kp Kd will be there, okay, but I know the EMF induced in per turn. EMF induced per turn is 2 volts. So basically this, right, actually they should have told like this formula is made for this 4.44 phi F into T. Then the EMF per turn here will be 4.44 phi into F into phi, right? This is the EMF per turn, okay? This is equals to 2. They should have mentioned it properly, but generally when they are talking about EMF per turn, then they don't include kpkt. Okay, now it's a single turn coils. Nothing is mentioned about the pitch. I have to assume kp to be 1. Nothing has been mentioned about pitch. Kp will be 1, but I know it's a single turn coil. Okay, single, it's uniformly wound. Okay, it is uniformly wound. If it is uniformly wound and it's a single phase turn, it is a uniformly wound. If it is uniformly wound, that means what will be your phase spread, right? So if it's uniformly wound, that means your m will be 1, right? If it's uniformly wound, m will be 1. What will be beta? So beta is equals to, beta will be what? Beta will be 180 divided by slots per pole. Now I know my kd formula is what? Kd formula is sine m beta, and it is uniformly wound, right? I will use the approximate formula, that is m beta divided by 2, right? So what is m beta basically? So m is what? M, I know m is equals to the number slots divided by pole into number of phase, right? And I know it is uniformly distributed. If it is uniformly distributed, that means slot per pole S by P will be what? S by P will be, or I can directly write what is xi, that is m beta. What will be m into beta? M into beta, slot by pole will get cancelled. It will be simply m beta will be 180 degree. This is also another formula, divided by phase. This is also very, very useful, right? 180 degree divided by number of phase. So in this case, number of phase is 1. So it will be simply 180 degrees, right? So now I will replace it. And remember, this should be in radians, okay? This should be in radians. This is outside sign. This should be in radians. So it will simply become sine of 90, right? This will be the sine of 90 divided by pi by 2, right? That is my kd. So I got my kd and I will replace it over here in this equation. So this value is this, sorry, this value is 2, kp is 1, kd is 2 by pi. So basically 2, so E per phase 2 into kp is 1 into 2 by pi. So it is 4 by, into number of turns is also there, because per turn voltage is 2, total I have t turns, so this will be into number of turns, right? So because here you see like this value is 2, this much value is 2, here already I have t, so I will just write here t, and this kp is 1 assumed because it is a full pitch, nothing has been mentioned. Kd I have found out, kd is 2 by pi. So this will be 4 by pi into t. So 4 by pi into t. What is 4 by pi? 4 divided by pi. So it is 1.273 number of turns. Okay, that is what my E phase is. So it is 1.273, that is option D. Okay, this question is again very good. Again we have made few assumptions. It is closer to uniformly distributed. That means your beta will be very low because your slots, number of slots will be very high. Then also we have derived this formula that m beta will be 180 degree divided by number of phase. If it is written over here, this should be in radians. this should be in radians, and this should be in degrees. Okay, so I hope it is clear, and we are done. We are basically done with our question and this chapter. So one more small miscellaneous topic is left, single phase motors, and then we will be able to finish our electrical machines subject. Thank you, and I will see you in the next lecture. Until then, happy learning.